Triangles. They seem so simple, right? Just three sides, three angles. But what if I told you that hidden inside this basic shape are these secret points of power, special centers that actually solve real-world problems involving fairness, balance, and even design? Today, we're going to unlock those secrets. Okay, let's jump right in. So let's kick things off with a classic dilemma. Let's say you and two friends all live in different houses. You want to find one single spot to meet up where the travel distance is exactly the same for all three of you. No arguments, just pure mathematical fairness. How in the world do you find that perfect point? Well, if we map it out, your three houses form the corners, or as they're called in geometry, the vertices of a giant triangle. The solution to your problem is hidden somewhere inside, or maybe even outside this very shape. Don't worry, geometry is coming to the rescue. And the answer to this whole puzzle is our very first secret center. It's called the circumcenter, and it is the key to finding that perfectly fair meeting spot. To find it, though, we're going to need a special tool. That tool is the perpendicular bisector. Now, I know it sounds a little technical, but the idea is actually super simple. For any line, like the path between your house and a friend's, the perpendicular bisector just slices it exactly in half at a perfect 90-degree angle. And what's cool is that every single point on that bisector is the exact same distance from both ends of the line. So how do we use it? Simple. We just draw the perpendicular bisector for each of the three sides of our triangle. And this is where it gets kind of magical. All three of those lines will cross at one and only one single point. And that point of intersection, that's our circumcenter. And that, right there, is its superpower. The circumcenter is the one and only point that is the exact same distance from all three corners of the triangle. So we found it. That is your perfectly fair meeting place. Problem solved. But here's where it gets really weird and interesting. For a normal-looking acute triangle, that spot is right there, inside. But for an obtuse triangle, that's one with an angle over 90 degrees, the fair meeting spot is actually outside the triangle. Can you imagine telling your friends, hey, to be fair, we have to meet over there, outside the neighborhood? And this isn't just a fun puzzle for planning meetups. Archaeologists use this exact same principle. Let's say they find three ancient stones they think were part of a circular monument. Well, they can treat those stones as the vertices of a triangle, find the circumcenter, and that tells them exactly where to start digging for the central fire pit. Pretty cool, right? Okay, on to our next puzzle. So we figured out how to find the point that's an equal distance from all the corners, but what if you need to find a point that's an equal distance from the sides of the triangle? To picture this, imagine a beautiful triangular park, and it's surrounded on all three sides by walking paths. Your job is to install a big fountain right in the middle. But to make it look perfect, the fountain has to be the exact same distance from each of the three paths. Where do you put it? You see, this is a totally different problem. The circumcenter was all about the corners, the vertices. Our next secret center, which is called the incenter, is all about the sides, the edges. It's a completely different kind of center. And for this new puzzle, we need a new tool, the angle bisector. And it does exactly what it sounds like. It's a line that takes an angle at a corner of the triangle and just splits it into two perfectly equal, smaller angles. Think of a hockey goalie. To defend the net, they instinctively position themselves on the angle bisector between the puck and the two goalposts. And why do they do that? Because any point on that line is the same distance from the two sides that form the angle. It gives them the shortest, most equal distance to move to block a shot, no matter which side it goes to. And just like with our first tool, if you draw the angle bisectors for all three corners of a triangle, yup, you guessed it, they also meet at one single amazing point. This point is the incenter, and that is the perfect spot for our fountain, the one location that's the same distance from all three paths. All right, so we've covered fairness from the corners, and we've covered fairness from the sides. Let's move on to our third and final secret center, which is all about pure physics and balance. Every physical object has a center of gravity. For a triangle, this balancing point has a special name, the centroid. If you were to cut a triangle out of a piece of cardboard, the centroid is that one sweet spot where you could put your fingertip underneath and it would balance perfectly flat. Now, to find this balancing point, we need our third tool, the median. A median is super simple. It's just a line that connects one of the corners, a vertex, to the exact midpoint of the side opposite it. Now, the centroid has a secret code, a kind of magic number that tells you its location every single time. And if there's one thing you remember from this section, it's this fraction, 2/3. This is what's known as the centroid theorem. It's a rule that says the centroid, that spot where all three medians meet, is always located exactly 2/3 of the way down any median if you start from the corner. It's not halfway, it's not 3/4, it is always precisely 2/3. And you actually see this principle in design all the time, probably without realizing it. Just look at this plate. Each triangular section is designed so its weight can be balanced. The whole thing is stable because the designers considered the centroids of these shapes. It's literally physics in action on your dinner table. So we found these three really powerful centers. But it's also worth remembering that you can't just take any three lines and make a triangle. There are some fundamental rules that govern whether they can even exist. And this is the biggest rule of all. For any triangle to actually be a triangle, the sum of any two sides has to be longer than the third side. Think about it. If you have sticks of length 5, 7, and 12, you can't make a triangle. Why not? Because 5 plus 7 only gets you to 12. The two shorter sides would just lie flat against the longest one. They can't pop up to form that third corner. And here's another cool rule called the hinge theorem. The easiest way to think about this is like a door hinge. You've got two fixed lengths, right? The width of the door and the wall. The more you open that door, making the angle bigger, the farther the edge of the door gets from the wall. That's all it is. If you have two triangles that share two equal sides, the one with the bigger angle squeezed between them will always have a longer third side. So we've explored three totally different secret centers. We've got the circumcenter for fairness from the corners, the incenter for fairness from the sides, and the centroid for perfect balance. They all seem to live in different places for different reasons. Which brings me to one final interesting question. Is there any special type of triangle where all three of these powerful points, the circumcenter, the incenter, and the centroid, all merge into one single ultimate center? I'll leave you to think about that one.